March 22, 1949. Veteran steam crews called the new EMD F7 a refrigerator car and refused to operate it. How did this mock diesel survive 500,000 miles while their beloved steam locomotives died at 200,000? The laughter from veteran railroaders echoed across the diesel service facility that morning. Everything about the F7 contradicted what steam crews understood as a proper locomotive. No massive driving wheels, no imposing boiler reaching 2 stories high, no rhythmic exhaust beats that announced a locomotive's presence miles before it appeared. Just a streamlined car body painted in Santa Fe's Warbonnet scheme, housing machinery that steam men dismissed as fragile and overcomplicated. Inside the cramped cab, conditions seemed designed to insult engineers accustomed to spacious steam locomotive compartments. The operating position measured barely 6 feet across, with controls mounted on a console that looked borrowed from a factory assembly line rather than a railroad. If you want to see more videos about old trains, make sure to subscribe so you never miss another video. Visibility came through narrow windshields that offered limited views compared to the commanding perspective steam cabs provided. No fireman's position existed because no fireman was needed, eliminating the camaraderie that defined steam operations. The diesel's appearance offended railroad traditionalists who had grown up admiring the mechanical artistry of steam power. Where massive connecting rods transformed reciprocating motion into rotational force through visible mechanical precision, the F7 hid its electric traction motors beneath an anonymous car body. Steam locomotives announced their power through clouds of smoke and thunderous exhausts. The diesel simply hummed with electric motors that seemed inadequate for serious railroading. Frank Sullivan's skepticism extended beyond aesthetics to fundamental questions about diesel reliability. Steam locomotives had hauled American freight for a century through every conceivable condition. Diesels represented unproven technology, promoted by manufacturers who claimed revolutionary advantages but couldn't demonstrate the long-term durability that railroads demanded. Santa Fe's management might be experimenting with these machines, but experienced crews knew that steam power would remain supreme because it always had. The specifications that mattered to Sullivan and his fellow steam engineers seemed deliberately modest. 500 horsepower from the F7's single prime mover compared poorly to the 5,000 horsepower that massive articulated steam locomotives developed at full throttle. Maximum speed of 65 miles per hour seemed unremarkable for machines that supposedly represented the future of railroading. The weight of 230,000 pounds felt insignificant compared to steam locomotives weighing twice that much. Tom Brennan had heard every criticism during the 3 weeks since EMD delivered the F7. His engineering team understood that convincing steam crews to operate diesels would be harder than any technical challenge. Railroad culture ran deep, and men who had spent careers mastering steam locomotive operations weren't about to embrace machines they viewed as toys built by companies that didn't understand real railroading. But Brennan had studied the F7's technical specifications with interest that went beyond surface appearances. The 567 cubic inch displacement prime mover represented evolutionary engineering from electromotive division, refined through years of passenger diesel operations. 16 cylinders arranged in a 45-degree V configuration delivered power through direct fuel injection that required no sophisticated electronic management. The simplicity was deceptive, hiding mechanical precision that steam locomotives couldn't match. The resistance Tom Brennan faced in March 1949 reflected railroad industry dynamics that had remained unchanged for generations. Steam locomotives had conquered American railroading through sheer mechanical reliability, proven across millions of operational miles. Every railroad operating department was staffed by men who had learned their trade maintaining, operating, and trusting steam power through conditions that destroyed lesser machinery. Richard Dilworth stood in Electromotive Division's LaGrange, Illinois headquarters that same March morning, reading telegrams from railroad mechanical departments that expressed growing frustration with diesel locomotive complexity. The messages shared common themes that threatened EMD's ambitious plans for diesel supremacy. Maintenance crews trained on steam locomotives struggled with electrical systems they didn't understand. Operating departments complained about diesel units that failed in ways steam locomotives never did. Accounting departments calculated that diesel fuel savings couldn't offset the higher initial purchase costs and specialized maintenance requirements. The fundamental challenge EMD faced involved convincing an entire industry to abandon proven technology for machines that represented complete operational philosophy changes. Steam locomotives failed in predictable ways that experienced crews could diagnose and often repair trackside using basic tools. Diesels required specialized electrical knowledge and sophisticated testing equipment that few railroad shops possessed in 1949. Baldwin Locomotive Works, the dominant steam builder for over a century, had responded to diesel competition with machines that reflected traditional railroad thinking. Their road diesels featured complex electrical systems designed by Westinghouse engineers who assumed railroads would maintain diesels like stationary power plants. Multiple control systems required constant adjustment. Electrical components failed in trackside environments where moisture, vibration, and temperature extremes destroyed delicate circuits. Baldwin's diesels worked when new but deteriorated rapidly under conditions that steam locomotives handled routinely. Alco GE diesels faced similar problems despite General Electric's electrical expertise. Their road switchers featured powerful 244 engines that developed impressive horsepower but consumed lubricating oil at rates that horrified maintenance departments. Electrical systems required specialists to diagnose problems that shut down locomotives for days while parts were ordered and installed. By early 1949, several major railroads had returned to steam locomotive production after disappointing experiences with early diesels that promised much but delivered operational headaches. Dilworth understood that EMD's F7 had to succeed where competitors failed, not through revolutionary technology, but through systematic attention to reliability that railroads demanded. The 567 engine represented EMD's answer to the fundamental diesel challenge. Instead of pursuing maximum horsepower through complex systems, the 567 delivered adequate power through mechanical simplicity that maintenance crews could understand and repair. The engine's design philosophy contradicted approaches that Baldwin and Alco pursued. 16 cylinders rather than 12 provided power redundancy. If one cylinder failed completely, the remaining 15 continued delivering usable power. Direct fuel injection eliminated carburetors that clogged in dusty railroad environments. Mechanical fuel pumps driven directly from the camshaft required no electrical systems to maintain precise injection timing. Cooling systems represented another area where EMD's conservative engineering philosophy diverged from competitors. The 567 featured oversized radiators that maintained optimal operating temperatures even when cooling fans failed. Water pumps were mechanically driven from the engine rather than electrically powered, eliminating failure points that stopped competitor locomotives. Every component was designed for accessibility, allowing maintenance crews to replace parts trackside rather than shopping locomotives for minor repairs. The F7's electrical system reflected similar attention to railroad operating realities. Traction motors were sealed units that protected electrical components from moisture and dust. Main generators featured brushes designed for 100,000 miles between replacements rather than the 20,000-mile intervals Baldwin units required. Control circuits used robust relays rather than delicate electronic components that failed when subjected to vibration and temperature extremes common in locomotive service. The EMD 567 engine that powered the F7 represented mechanical philosophy that contradicted diesel development trends in 1949. While competitors pursued higher horsepower through increased cylinder pressures and complex fuel systems, EMD engineer Richard Dilworth had designed an engine that prioritized longevity over peak performance. The result was machinery that seemed unimpressive on paper, but delivered reliability that revolutionized diesel locomotive economics. Each cylinder displaced 567 cubic inches, giving the engine its designation and providing the foundation for power delivery that remained consistent across hundreds of thousands of operational miles. The V16 configuration created a compact power plant that fit within the F7's streamlined car body while maintaining perfect mechanical balance. Firing order was carefully calculated to minimize vibration that destroyed competitor engines operating at sustained high outputs. Dilworth's fuel injection system eliminated every component that could fail in railroad service. Direct injection meant diesel fuel entered cylinders at precisely calculated moments based purely on mechanical cam timing. No carburetors to clog with dust, no electronic sensors to fail in extreme temperatures. Just hardened steel cams machined to tolerances measured in 10,000ths of an inch, rotating at speeds that ensured consistent fuel delivery regardless of ambient conditions. The fuel pump design revealed EMD's systematic approach to reliability. Each cylinder had its own injection pump driven directly from the camshaft through a gear train that required no adjustment once properly assembled. Fuel pressure reached 2,800 pounds per square inch through spring-loaded plungers that maintained precise delivery across the engine's operating range. If one pump failed, the other 15 continued operating normally, allowing the locomotive to maintain reduced power rather than shutting down completely. Lubrication systems incorporated redundancy that steam locomotive designers would have recognized and appreciated. The oil pump was gear-driven from the crankshaft, making oil pressure mechanically linked to engine speed. Full-flow oil filtration protected bearings from contaminants that destroyed competitor engines. Oil capacity reached 300 gallons, providing thermal mass that stabilized operating temperatures during sustained heavy loading. Cooling presented challenges that had defeated earlier diesel designs. The 567 generated substantial heat during continuous operation at rated power, and maintaining optimal temperatures required cooling capacity that exceeded what automobile-style radiators could provide. EMD's solution involved massive radiator sections mounted in the locomotive's roof, creating cooling surface area that handled heat rejection even when ambient temperatures exceeded 100 degrees Fahrenheit. The radiator fans were belt-driven directly from the engine, eliminating electric motors that consumed power and created failure points. Fan speed increased automatically with engine RPM, providing maximum cooling precisely when heat generation peaked. The system required no thermostats, no electric controls, no sophisticated management systems, just mechanical relationships between engine speed and cooling capacity that worked reliably across every operating condition railroads encountered. Maintenance access reflected railroad, operating realities that Dilworth understood from years consulting with mechanical departments. Major components could be replaced without removing the engine from the locomotive, individual cylinder heads unbolted for servicing without disturbing adjacent cylinders. Fuel pumps, water pumps, and oil pumps were accessible from walkways alongside the engine, allowing repairs trackside rather than in shop facilities. The 567's durability specifications seemed conservative compared to competitor engines, but Dilworth had designed for continuous operation rather than peak performance. Maximum continuous rating of 1,500 horsepower at 800 RPM meant the engine operated well below stress levels that caused premature wear. Piston speeds remained modest, reducing bearing loads and extending component life. Every design decision prioritized running 500,000 miles between major overhauls rather than achieving impressive dyno test results. The confrontation Tom Brennan had been dreading arrived on April 5, 1949, when Frank Sullivan and his engineer Bill Harrison refused to take F7 number 100 out on its first scheduled freight run. The two men stood in the Argenton Yard diesel facility, arms crossed, while Brennan explained that diesels were the future whether they liked it or not. "I'm an engineer, not an electrician," Harrison stated flatly. "Steam locomotives, I understand. You got a hot bearing, you can hear it. Injector fails, you can see it. This thing quits, I won't even know what's broken until some college boy with a voltmeter shows up to tell me." The resistance reflected genuine concerns that extended beyond traditional preference for steam power. Harrison had spent 22 years operating locomotives where mechanical failures announced themselves through visible and audible symptoms experienced crews could diagnose. The F7's sealed car body hid its machinery behind sheet metal panels that prevented the visual monitoring steam engineers relied upon. Electrical failures could shut down the locomotive without warning, leaving crews stranded with no ability to make trackside repairs. Santa Fe's solution involved mandatory diesel training that veteran engineers resented as insulting to their professional expertise. 3-day courses attempted to teach electrical fundamentals to men who had never needed to understand voltage, amperage, or circuit resistance during careers built on steam locomotive mastery. The training highlighted how completely diesels diverged from steam operations rather than building confidence in the new technology. The F7's first revenue runs confirmed Harrison's worst fears about diesel fragility. Unit 100 failed 47 miles into its maiden Chicago-Kansas City freight assignment when a traction motor brush holder cracked, creating electrical shorts that shut down all power delivery. The locomotive coasted to a stop on the main line, blocking traffic while steam power was summoned to rescue the stranded diesel and its train. Maintenance crews discovered additional problems as more 7 units entered service throughout April and May. Cooling system leaks developed in radiator sections subjected to vibration that steam locomotive water systems handled routinely. Generator brushes wore faster than EMD specifications predicted when locomotives operated in dusty Kansas wheat country. Electrical control circuits occasionally failed in ways that required complete unit shutdowns rather than the degraded but functional operation that steam locomotives provided when components failed. By June 1949, Santa Fe's operating department was documenting diesel reliability that fell far short of steam locomotive standards. F7 units averaged 285 miles between failures requiring mechanical department intervention. Steam locomotives on comparable assignments averaged 1,100 miles between similar issues. The diesel spent 18% of their time unavailable for service due to repairs. Steam power typically achieved 93% availability through maintenance practices refined over decades. Frank Sullivan's predictions about diesel inadequacy seemed validated by early operational experience. The machines looked modern and promised revolutionary advantages, but actual performance revealed that EMD hadn't solved the fundamental reliability problems that made diesels unsuitable for serious railroading. Steam locomotives might require more intensive maintenance, but they delivered predictable service that freight operations depended upon. Tom Brennan faced mounting pressure from Santa Fe's executive management to justify continued diesel purchases when steam locomotive builders offered proven technology at lower initial costs. The F7's theoretical fuel savings couldn't overcome the reality of units sitting in repair tracks while freight traffic waited for available steam power to move trains. Baldwin's sales representatives were making increasingly persuasive arguments that modern steam locomotives represented safer investments than experimental diesels that failed in daily service. The transformation began quietly during summer 1949 as F7 units accumulated operational miles that revealed patterns invisible during early service. Tom Brennan's maintenance teams discovered that many early failures resulted from improper handling by crews accustomed to steam locomotive operation rather than inherent diesel weaknesses. Engineer Bill Harrison had been operating F7 number 100 with throttle techniques learned on steam power, making abrupt power applications that caused electrical surges through traction motor circuits. Steam locomotives tolerated rough handling because mechanical components absorbed shock through their mass. The F7's electrical systems required smoother throttle transitions that allowed generators and motors to stabilize before accepting full load. Brennan instituted revised diesel training that emphasized operational differences rather than attempting to teach electrical theory to skeptical steam engineers. Smooth throttle applications, gradual dynamic brake engagement, allowing traction motors to cool between heavy grades. The techniques seemed minor compared to steam locomotive procedures, but they dramatically improved diesel reliability. By September, F7 units operating under revised procedures demonstrated performance that contradicted early failure rates. Number 100, once the symbol of diesel inadequacy after its maiden voyage breakdown, logged 3,200 miles between failures during August. The mechanical department discovered that most issues involved minor electrical adjustments rather than component failures requiring extensive repairs. The real revelation came from long-haul freight assignments where diesel advantages became undeniable. Santa Fe's Chicago to Los Angeles Super C merchandise train covered 2,227 miles in 40 hours, requiring locomotive changes every 300,400 miles when steam-powered. F7 sets made the entire run without unit changes, simply adding and dropping units as power requirements changed along the route. Frank Sullivan rode the Super C's cab through New Mexico in October 1949, experiencing diesel operation on exactly the kind of high-speed freight service where steam locomotives excelled. The F7 maintained 70 miles per hour across level track sections where steam power typically struggled to exceed 55 mph, while consuming water and coal at rates that required frequent servicing stops. Through Raton Pass, where steam locomotives battled 3,005% grades with helper engines pushing from behind, the F7 set climbed steadily without assistance. Sullivan watched the ammeter needles indicating traction motor load, seeing electrical current flow that represented power delivery. Steam locomotives couldn't match. The diesels weren't working harder than steam engines. They were simply delivering consistent power that didn't diminish as water and coal supplies depleted. The fuel economy Sullivan had dismissed as theoretical marketing proved devastatingly real during cost accounting that fall. The Super C's diesel operation consumed $847 in fuel for the Chicago-Los Angeles run. Comparable steam operation required $2,340 in coal and water while needing 9 locomotive changes that added 4 hours to transit time. The difference wasn't marginal improvement. It was a transformation of freight economics that steam power couldn't overcome. By December 1949, F7 number 100 had accumulated 52,000 miles with only 3 failures requiring shopping. The 567 engine showed no measurable wear despite continuous operation at power outputs that would have required steam locomotive overhaul. Traction motors operated within temperature specifications even during sustained mountain grades. Electrical systems that initially seemed fragile had proven robust when operated according to diesel requirements rather than steam locomotive habits. The reliability data convinced Santa Fe management to accelerate diesel purchases. Orders for 200 additional F7 units represented commitment to technology that had proven itself through operational performance rather than manufacturer promises. Steam locomotive production at Santa Fe's Topeka shops ceased permanently in January 1950, ending a century of steam-powered dominance. The industry-wide comparison that emerged during 1950 revealed why EMD's F7 succeeded where competitors struggled. Baldwin's road diesels, impressive during demonstration runs, deteriorated rapidly under sustained railroad service. Their Westinghouse electrical systems required constant attention from specialists who couldn't diagnose failures trackside. By mid-1950, several railroads had stored Baldwin units as maintenance nightmares while expanding F7 fleets. Pennsylvania Railroad's experience with competing diesels illustrated the differences that separated reliable from troublesome machines. Their Baldwin DR64 2000 units averaged 178 miles between failures during their first year of service. Electrical problems accounted for 67% of failures, with traction motor issues causing the majority of service disruptions. Maintenance costs reached $1.47 per mile, exceeding even intensive steam locomotive servicing expenses. The same railroad's F7 units logged 891 miles between failures, while accumulating operational experience. Electrical problems represented only 31% of issues, with most involving minor adjustments rather than component replacements. Maintenance costs stabilized at $0.63 per mile, providing the economic advantages diesels promised but competing manufacturers couldn't deliver. Alco's road switchers faced different but equally serious reliability challenges. Their 244 engines developed impressive horsepower but consumed lubricating oil at rates that shocked maintenance departments. Units required oil additions every 200 miles during heavy service, creating servicing demands that negated diesel efficiency advantages. Turbochargers failed regularly, shutting down locomotives until replacement units could be installed by specialists. The 567 engine's conservative design philosophy proved superior to competitors pursuing maximum performance. F7 units operated in 200 miles between oil changes using conventional petroleum lubricants. No turbochargers meant no high-speed rotating assemblies to fail in dusty environments. Power output remained constant across the engine's service life, while competitor units showed declining performance as components wore. Union Pacific conducted systematic testing during 1951 that quantified differences between diesel manufacturers. Their evaluation compared F7s against Baldwin and Alco units on identical assignments hauling freight across Sherman Hill's demanding grades. The F7s completed test runs consuming 12% less fuel than Baldwin units while maintaining schedules 8% faster. Alco units consumed 15% more fuel than F7s while requiring helper engines on grades the EMD units handled unassisted. Most revealing were long-term durability comparisons as units accumulated high mileage. By late 1952, some F7 units had exceeded 400,000 operational miles, with original 567 engines showing minimal wear. Baldwin units typically required major overhauls by 150,000 miles. Alco 244 engines needed rebuilding around 200,000 miles. The maintenance interval differences created cost disparities that made F7s overwhelmingly economical despite higher initial purchase prices. Southern Pacific's mechanical department documented the maintenance hour differences during 1952 annual reports. F7 units required 0.87 maintenance hours per 1,000 miles operated. Baldwin diesels needed 2.34 hours. Alco units demanded 1.96 hours. The labor cost implications extended beyond direct maintenance expenses to availability rates that determined how many locomotive railroads needed to maintain service schedules. The telegram that arrived at EMD's LaGrange headquarters on November 3, 1954, carried information that would transform diesel locomotive industry standards. Santa Fe Railway Mechanical Department reporting F7 Unit 100L exceeding 500,000 miles operational service. Original 567 engine, original main generator, original traction motors. No major component failures. Request EMD engineering inspection to document. Achievement. Richard Dilworth traveled to Argentine Yard personally to witness what his conservative engineering philosophy had accomplished. Unit 100L sat in the diesel service facility, externally showing 5 years of hard railroad service but mechanically sound in ways that contradicted everything railroads understood about locomotive longevity. Steam locomotives required complete rebuilding around 200,000 miles. Early diesels from competing manufacturers needed major overhauls by 150,000 miles. The F7 had doubled those standards while maintaining performance specifications. The inspection revealed engineering decisions that explained extraordinary durability. The 567 engine showed cylinder bore wear of only 0.03 inches, well within acceptable limits for continued operation. Piston rings retained proper tension. Bearings displayed normal wear patterns without scoring or distress. Dilworth's measurements confirmed that the engine could operate another 500,000 miles before requiring major overhaul. Traction motors told similar stories of conservative design proving superior to aggressive performance targets. Commutators showed minimal wear despite hundreds of thousands of power applications. Armature windings tested within original electrical specifications. Ball bearings retained proper clearances. The motors that competitors rebuilt every 100,000 miles were essentially new mechanically after 500,000 miles of freight service. Main generator inspection produced the most impressive findings. Brushes showed normal wear requiring routine replacement, but commutator surfaces remained smooth and true. Field windings tested at full insulation resistance values. The generator that powered traction motors through mountain grades and desert heat had survived conditions that destroyed competitor electrical systems through systematic attention to thermal management and component quality. Santa Fe's operating department data revealed how 500,000-mile reliability transformed diesel economics. Unit 100L's total maintenance costs averaged $0.58 per mile across its service life. Comparable steam locomotive operation on identical assignments cost $1.73 per mile, including fuel, water, servicing, and repairs. The diesel advantage wasn't marginal efficiency improvement. It was a fundamental transformation of railroad operating economics that made steam power obsolete. By 1955, the railroad industry acknowledged that EMD's F7 had established diesel locomotive standards that competitors couldn't match. Baldwin Locomotive Works, dominant steam builder. For a century, discontinued locomotive production entirely. Alco struggled to redesign their road diesels to achieve F7 reliability levels but never succeeded in matching EMD's systematic engineering approach. The transformation extended beyond simple technology replacement. F7 units enabled freight service improvements impossible with steam power. Transcontinental trains operated with single locomotives consist from origin to destination. Helper districts were eliminated as diesels climbed grades. Steam locomotives couldn't handle unassisted. Servicing facilities shrank from massive roundhouses to simple fueling and sanding tracks.